Hello and welcome to this course, Top 10 Best Practices for Today's Homebuilder. Learn the latest and greatest techniques being used today to build better homes. My name's John Spillman and I'll be your instructor for this course. This course is brought to you by Better Built Northwest, which is a program created and supported by the Northwest Energy Efficiency Alliance. As a market resource, Better Built Northwest is committed to accelerating the adoption of the most energy efficient building practices in residential new construction. Better Built Northwest is a core component of the Northwest Energy Efficiency Alliance's residential new construction program. Northwest Energy Efficiency Alliance, also known as NEA, is an alliance of more than 140 utilities and energy efficiency organizations working on behalf of more than 13 million energy consumers. NEA is dedicated to accelerating both electric and gas energy efficiency, leveraging its regional partnerships to advance the adoption of energy-efficient products, services, and practices. Since 1997, NEA and its partners have saved enough energy to power more than 700,000 homes each year. As the second largest resource in the Northwest, energy efficiency can offset most of our new demand for energy, saving money and keeping the Northwest a healthy and vibrant place to live. At BetterBuiltNW.com, you can find the resources you need to build energy-efficient homes. Here is an overview of the course. We'll be looking at the benefits of building high-performance homes and the third-party verification when you participate in local energy efficiency programs. We'll cover the basics of building science, and then we'll dive into 10 categories of good, better, and best practices for building high-performance homes. Towards the end, we'll show you how to explore local energy efficiency programs and potential financial incentives. And finally, we'll give you tips on implementing quality assurance procedures and techniques to help ensure your project achieves your high-performance goals. So to cover any of the topics in great detail would require a full-day class for each and every topic. So what we'll present is a survey of the various options in the top 10 categories, and the good, better, and best spectrum of options are provided with the intention to meet all levels of experience with building high-performance homes. And this is intended to chart a course to help you navigate some of the profound changes ahead in the construction industry. Specific information on construction details, material characteristics, and equipment selection are available by consulting your local energy rater verifier. At the end of the course, we'll provide links to additional online resources and trainings. Our learning objectives are to identify common barriers to energy-efficient home construction, learn building science and moisture management basics, gain approaches to improve envelope design and performance, review advanced mechanical systems, lighting, and appliances, and learn how to leverage local utility programs and energy efficiency incentives. And finally, we want to learn about Better Built Northwest's resources and training opportunities. Let's begin by looking at the opposite of high-performance homes, in poor-performing home scenarios, to think about why you should want to build to a high-performance level to benefit your business. What's the business case for making these changes? By taking performance to the next level, you can limit your liability and preserve your profits. Callbacks can result from poor design, the wrong material selection, but oftentimes it results from incorrect installation of systems designed to safeguard the structure. In this example, there was a missing kick-out flashing at the roof-wall interface. Bulk water flowed down the siding and it clinged to the wall with surface tension. Eventually it penetrated the wall, causing serious structural damage. And durability problems can often be linked to energy loss. Here we see examples of ice dams forming because of heat loss in the attic. This problem is preventable by simply installing the standard air sealing and insulation materials correctly so that we manage heat transfer from the conditioned space to the attic. The photo on the left is of a newly constructed home in Bend, Oregon that is not performing very well. Another reason to build high-performance homes is health. Unhealthy indoor air can stagnate in poor-performing homes, which may result in sick customers. Asthma rates continue to climb in the U.S. every year. Poor indoor air quality can cause this disease, and the average American spends 90% of their time indoors, and a large amount of that time is in our homes. You want your reputation to be connected with healthy homes that provide fresh and clean indoor air. Poor performing homes can result in uncomfortable customers, and of course this will never lead to word-of-mouth referrals or positive reviews. With today's evolved materials and building techniques, an uncomfortable home is unacceptable and totally preventable. High energy costs will also cause dissatisfaction with home buyers. Oversized HVAC equipment leads to short cycling, which can significantly lower the rated efficiency of the equipment and results in high energy bills. Why pay for this excess fuel when a well-built building shell with high levels of insulation and proper air sealing can lower the design load and allow for smaller equipment to do the job more efficiently and at a much lower cost to operate? Housing affordability involves more than just the dollars per square foot of initial cost to build the home. When looking at the total cost of ownership, you need to consider the monthly operating cost as well, including energy bills, water and sewer bills, maintenance and upkeep, as well as location and the transportation costs of living in the home. Low-income people spend a much higher percentage of their income on energy. So lowering the energy bills to operate the home can change this equation. High-performance energy-efficient homes can be more affordable in the long run. And the same is true for first-time home buyers. Lower energy bills frees up money that can be used towards a mortgage payment. This makes the first-time home purchase more viable for the younger generation. There are so many dynamics and forces at play in a home that can cause any number of poor performance issues we just described. This is why it's important to take a whole systems approach, known as the house as a system, when building in order to achieve a high-performance home. We'll look closer at this comprehensive approach to building a house in this course. Now let's look at where the market is headed, which you'll see provides more reasons to think about building high-performance homes. Buildings in the U.S. offer a big opportunity for all of us to reduce wasted energy and lower carbon emissions. Buildings use 76% of all the U.S. electricity consumed in a year and 40% of all the energy use. However, by 2030, building energy use could be cut by more than 20% using technologies known to be cost-effective today. This pie chart shows the breakdown of how energy is produced across the Pacific Northwest region. The Pacific Northwest utilities have met much of the demand for energy load growth as the economy grew from 1978 to present through energy efficiency conservation programs. Since 1978, the region has met over half of its load growth through energy efficiency resources, which resulted in $4 billion being saved on energy bills, and enough energy to power 5 cities the size of Seattle. Energy efficiency is also very cost-effective. The average cost to produce electricity for future load growth by saving a kilowatt with energy efficiency upgrades is less than 3 cents. Compare that to the average cost to produce electricity at around 10 cents per kilowatt hour when it's generated in a newly built coal or natural gas-fired plant. It makes sense to conserve energy for the bottom line of the utilities. Plus, if the utility companies do not have to build new power plants because we reduce the wasted energy in the system, it keeps energy costs lower for everyone. Home buyers are identifying year after year in greater numbers as wanting energy efficiency in the homes they buy. The study asked how likely they would be willing to pay more for a high-performance home that costs more upfront but would have lower monthly utility bills, and 81% responded that they were willing to pay more for this benefit. It's also worth noting that in this example, they only focused on the dollar savings as the primary benefit, but never mentioned comfort, quality, or health, which likely would have driven these numbers even higher if these benefits were included in the stated question. And builders across the nation are responding to these buyers' expectations. In the 2017 National Association of Home Builders Green Smart Market Report, we see steady growth of builders and remodelers who say they are incorporating green building materials and techniques into their projects. That same study also reported that the more green experience a builder has, the more they appreciate certifications, the easier they think it is to market green, and the less they perceive the incremental cost to be. 91% of dedicated green builders say customers will pay more for green homes. The next market trend to be aware of is the zero energy home, which is a home that generates as much energy on site as it uses over the course of a year. And these zero energy homes are being built in greater numbers across markets in the U.S. We'll look at the zero energy home in more depth in Section 10 of this training. Policy changes are also moving the market towards high-performance buildings. In the state of Washington, the energy code cycles are evolving to require all newly constructed homes to be built zero energy by the year 2030. In Oregon, the policy changes include a goal of all newly constructed homes to be built to the US DOE Zero Energy Ready standard by the year 2023. Additionally, the City of Portland Home Energy Score program is helping to motivate homeowners of existing homes to make cost-effective upgrades to their homes in order to achieve higher levels of performance, greater comfort, and healthier indoor air. We're seeing the new home market moving towards higher and higher performing homes through a pull and push dynamic. As energy codes increase requirements for greater energy efficiency, they pull the market forward, whereas voluntary energy efficiency programs with cash incentives tend to push the market towards the newest, cost-effective strategies to improve energy efficiency to levels above code requirements. We often hear that the construction industry is slow to change, and that may have been true at one time, but today's materials, equipment, markets, and just about everything is changing rapidly. Builders and tradespeople need up-to-date information and advice, and that is readily available through these types of programs. The benefits to the builder are many, but one of the most important is an added level of quality assurance. Verifiers provide another set of eyes on the project to help ensure that all the subcontractors have done their jobs correctly. There's also performance testing that gives the builder feedback. All of this results in a better product delivered to the customer with lower risk and reduced callbacks. They can help you avoid embarrassment when turning the keys over to a buyer if something wasn't done correctly and the home buyer points it out to you later. Verifiers find issues all the time during their inspections, such as missing insulation, the wrong equipment installed, or the equipment installed incorrectly. These problems often happen because of communication gaps, but sometimes it's a training-related issue. The verifiers are there to find the issues and help the builder to resolve the problems in the current and future projects. Here's a short list of what the verifier does on the project. They conduct performance testing, including duct air leakage tests, building air leakage tests, and ventilation performance tests. They'll check insulation levels and quality of placement. They'll pay attention to air sealing details and the durability details during construction. They'll verify ventilation operation for the whole house ventilation to ensure indoor air quality. And they'll review the HVAC system sizing documents provided by the heating contractor. Another benefit to the builder and their sales professionals is marketing help. Green building and energy efficiency programs often provide sales and marketing collateral to help showcase the improved quality and energy efficiency of the home. Not only does this help sell the house, it also differentiates the builder's company as a leader in the marketplace. Another example of this is in Oregon and Southwest Washington. For newly constructed homes, the Energy Trust of Oregon's EPS New Construction Program provides the Energy Performance Score to participating builders. The EPS is an energy label that can be used to make the largely invisible energy efficiency features visible when potential buyers visit the home. It shows estimated operating costs, energy use, carbon footprint, and the efficiency features built into the home. EPS is just like a car's miles per gallon rating, but for the home. Another energy label you can use is the HERS index. HERS stands for Home Energy Rating System. A builder can demonstrate energy efficient features in their homes with an independently verified HERS index rating. The HERS index is a simple, easy to understand system for prospective homebuyers, realtors, and appraisers to compare the energy performance of homes. The HERS index score comes from ResNet, the Residential Energy Services Network. Again, energy labels, like the HERS index, are like a miles per gallon rating for homes that can help you show the energy efficiency built into your projects. Builders of high-performance homes can earn a federal tax credit for each qualifying project. The 45L federal tax credit requirements are to have an energy model completed that demonstrates a 50% improvement compared to a 2006 IECC code baseline home, with at least 20% of the energy reduction resulting from the improvements to the building shell. The energy model must be conducted by your verifier or a HERS rater. Contact your verifier to learn more. Or if you need to find a verifier to work with, you can use the Find a Professional search on BetterBuilt Northwest. In this next section, we're going to cover the building science fundamentals that govern the natural forces acting upon the home. These are the forces we want to control wherever possible in order to build a high-performance home. So what is building science? Well, building science studies the interactions of people living in the structure, the components of the structure and the systems within it, and the physical phenomenon affecting the building. The laws of nature govern how heat, air, and moisture move around and through the structure of the building. So by gaining a working knowledge of these laws, we can build in better control mechanisms to manage the heat, air, and moisture movement. Let's start with the physical phenomenon that the house is experiencing. Pressure differentials, temperature, humidity, air movement within the structure, and how all these forces affect the building and the occupants. It sounds much like the 6 o'clock weather report. Today we can expect a high of 68 with lows around 60. There'll be high pressure dominating around the ceiling with lower pressures near the foundation zones. High local relative humidity levels are approaching 50%. There are two laws of thermodynamics that govern most of these forces, which can be restated in a very easy to understand set of basic principles. If you can remember these basic principles, you've got it. The two laws of thermodynamics in a nutshell. Apply these principles to any situation involving energy, air, or moisture movement in a building, and you should be able to predict the direction of that movement. The first basic principle is warm moves to cold, or another way to put it is heat chases cold. This is from the first law of thermodynamics. Energy in the form of heat will always move from a warmer mass to a colder mass. Next is more moves to less, from the second law of thermodynamics. Typically in a building, this is seen in concentration of molecules. For example, moist air with more vapor molecules will move towards drier air if given the opportunity. Of course, this has implications for how we manage moisture in the form of vapor. Next is high moves to low. Air pressures will always move from an area of high pressure to an area of low pressure. This affects how air and moisture move through the structure. Then there's another scientific law that we must pay attention to, Newton's law of universal gravitation. Gravity moves everything down and is key for proper moisture management of bulk water to keep it away from the wooden structural elements of the building. So what is the one thing in common with all of these principles? The answer is movement. These laws all describe movement, and it is this movement that we focus on with building science. Any questions on the basic principles? If not, class is dismissed. Just kidding. So let's get into some of that movement and begin with moisture flows. Water really is amazing. It has three properties that give it unique characteristics: cohesion, adhesion, and surface tension. Cohesion is where water is attracted to water. Surface tension happens because of the 104-degree angle of the hydrogen and oxygen atoms, which polarizes the molecule and makes it very cohesive or sticky. It acts much like a magnet does with a positive and a negative side. The cohesive forces between liquid molecules are responsible for the phenomena known as surface tension. It's because of surface tension that some bugs can walk on water. Adhesion is where water is attracted to other substances. And this adhesion is something to pay close attention to as we design and build systems to keep water running off and away from the building. Flashing with a drip edge is an example of a product that is designed to prevent water adhesion from wetting the outside of our buildings. Kick-out flashing, which is designed to direct roof runoff away from a sidewall and direct it into the gutter, is another good example. What are the ways that moisture can flow? Well, liquid water can move by gravity, but it can also move by pressure differences, the high moving to low. Liquid water can move by capillary action, and that's the ability of liquid to flow against gravity, where liquid can spontaneously rise in a narrow space like a thin tube, or in porous materials such as paper, or in a building through concrete. Water as a vapor generally moves in two different ways. Water vapor is either transported through air movement, or water vapor can diffuse through solid materials, molecule by molecule through the pores of that material. Of course, we need to keep our structures dry to prevent decay. And wood-destroying insects and organisms need all three of these conditions in order to thrive and damage the building. Temperature needs to be warm, there needs to be available food, and there needs to be available moisture. If we take away one of these conditions, they will not be able to take up residence and cause decay. Well, temperature varies considerably, plus we humans like to be warm, so that one's not the best choice. Food is what most of our buildings are made of. Wood is our structure, but to the decay organisms, that's dinner. So that leaves moisture as the best candidate for effective regulation and why we spend so much of our effort to keep our buildings dry. So how much water is too much when we want to prevent decay? Well, fiber saturation is the level of moisture content where the cell walls of the wood are holding as much water as they can. Water held in the cell walls is called bound water, while water held in the cell cavities is called free water, and as the name implies, the free water is relatively accessible as a source of water for decay. So decay can generally only get started if the moisture content of the wood is above the fiber saturation of 28% moisture content by weight. Now, wood does have a buffering ability where it can absorb and store moisture, then release it during dry periods without harm to the wood, as long as the wood does not reach the 28% saturation rate and remain saturated for long periods, creating those conditions for insects, mold, or fungus to begin decay. So building structures that allow for drying is crucial to long-term durability. So that water storage capacity of wood acting as a buffer for short periods of time can add up to be quite a bit of water. A 2,000 square foot wood-framed house can store and release up to about 50 pounds of water. You can use a pin-type moisture meter to measure the wood moisture content at the time of construction. It's important to measure the structural framing prior to insulation and sheetrock, and we want the moisture levels to be optimally below 19% before cover. All builders should own one of these and use them on every building prior to cover. Not only is it best practice, it's required by the Oregon Residential Specialty Code for those building in Oregon. For bulk water management, we use the WRB, or the weather resistive barrier, under the siding to keep the walls dry if wind-driven rain or snow hits the walls and migrates behind the siding. To take that protection to the next level, many builders are adding a rain screen detail behind the siding. By installing furring strips between the WRB and the siding, a drainage gap allows for any wind-driven water that penetrates the siding to drain quickly down and away from the wall. Another way to build a rain screen is to use a WRB product that has the offset built in with dimples, mesh, ribs, or something similar to create the drainage channels. With the addition of a ventilation gap at the top of the rain screen cavity, you can make a ventilated rain screen. This gives a secondary level of drying potential because now air can flow up through the rain screen gap and dry out moisture even faster. And this detail can help the interior section of the walls dry faster if any moisture penetrates the wall in the future. And then there's the capillary action we need to guard against, which again is the water molecules moving through porous materials. This moisture flow is powerful and can even defy gravity to move water upward. And this is why capillary breaks are required between concrete and wood. Without this detail, moisture could wick up from the concrete into the wood and cause decay if the soil in the location is wet. When it comes to water in its vapor state, we need to guard against the two ways it can move, and that is by diffusion or by air movement, also known as convection. By diffusion, vapor molecules can travel alone, and vapor will diffuse through permeable materials. It passes molecule by molecule through the pores of the material. So as we choose materials that make up the layers of our building assemblies, we need to understand the permeability of those materials. The perm ratings will tell us if the material is impermeable, semi-impermeable, semi-permeable, or permeable, as we can see in this table. Vapor retarders, installed on or just inside the interior layer, usually fall into the impermeable or semi-impermeable category, depending on the climate zone. The vapor retarder is used to guard against vapor diffusion of moist indoor air to keep it out of the wall cavity. However, when we start choosing materials to be installed on the exterior of the building, it's best practice to choose a semi-permeable or permeable material in order to provide drying potential to the outside. And this can safeguard the wall assembly in the future in case any vapor does enter the wall from diffusion, air leakage, or if you have a bulk water leak at a window or something like that. We also need to guard against water vapor convection. That is vapor moving along with air molecules, which will flow from areas of high pressure to low pressures, one of our basic principles. The pressure differentials will always even out over time. And that is because water vapor can hitch a ride along with the air molecules moving from high to low through pathways like cracks, gaps, or holes in the air barrier. So air sealing the building shell helps increase energy efficiency, but as we can see here, it also protects the building structure from potential moisture damage. So clearly we need to protect the building from both vapor diffusion and vapor convection. Which of these two forces poses the greater threat? Well, a leading building science expert, Building Science Corporation, conducted a lab experiment to measure the amount of moisture that could penetrate a wall over the course of one heating season. They ran two simulations, one for diffusion and another by convection. For the first, they used a full 4x8 piece of sheetrock and subjected it to simulated conditions that you would find in a typical home of 70 degrees Fahrenheit and 40% relative humidity levels. After the heating season, they measured about 1/3 of a quart of water had migrated through the sheetrock to the interior cavity of the wall. So diffusion can add up some water content over time. The second wall test, again, used a full 4x8 piece of sheetrock, subjected to the same 70 degrees and 40% relative humidity conditions. But this one had a 1 square inch hole through the sheetrock and positive air pressure that can be found in houses, conditions that would cause air leakage through that hole. What they found after one heating season with air leakage was the amount of water that migrated into the wall was 90 times greater, with 30 quarts or 7.5 gallons of water that was able to enter the wall. So air leakage is a far greater threat to the long-term durability of the structure, and air sealing is key to safeguarding the wood in our building assemblies. So next up is our vapor quiz. What is lighter, dry air or humid air? We'll have a look out the window up to the sky, and the clouds we see show us that moist, humid air is actually lighter than dry air. It kind of seems to defy common sense, but the reason that happens is air in our atmosphere is 78% nitrogen and 21% oxygen. And nitrogen is quite heavy at the atomic level, especially compared to a water molecule. Nitrogen is at 28 atomic units and a water molecule is 18. So as the lighter vapor molecules enter the air, they rise to the top and they displace the heavier, drier air with all of that nitrogen, and that sinks. So what are the implications in our structures? Holes in the air barrier up high are going to be more vulnerable to vapor convection. So think, for example, recessed can lights in a kitchen cathedral ceiling. You don't want air leakage happening there. There's going to be moisture in the air from the cooking activities, and there's going to be a driving force up at the ceiling plane, and that's likely to enter into the building assembly and cause damage. So you don't want air leakage anywhere in the structure, but you really don't want it high in the structure. So now let's look at relative humidity, and this is the term that describes the amount of water vapor that exists in a mixture of air and water vapor. It changes with temperature. So for example, the same amount of water vapor that is at 100% relative humidity at 50 degrees can have only 28% relative humidity at 86 degrees. And this is because the air will expand as it warms, so the concentration of water in a given volume goes down. When relative humidity is at 100%, like it is at 50 degrees in this example, it can change from a water vapor back to a liquid. And we've all experienced this. Just think of the moisture that drips down the side of the can on your favorite cold drink. This is water vapor coming in contact with the cold aluminum can and changing back to liquid. And of course, this is what we're trying to prevent happening in our walls and other building assemblies, since the outer layers, like the sheathing, will be colder in the winter. And if water vapor can get to that cold surface, it can condense to liquid if the temperature is cold enough and at or below what we call the dew point temperature. The optimum relative humidity that we'd like to keep our homes at is between 30 and 50%, and this is where we find it the most comfortable and healthy. Above 50 or 60%, and we can start seeing condensation in cold places that usually gets noticed when mildew or mold starts growing. As we wrap up the building science section on moisture flows, we have seen there are many ways water can cause problems for our structures, but the solutions for controlling the moisture are available. We simply need to choose the right materials and install them correctly to safeguard the structure and build a high-performing house. We also need to make sure to use materials that allow the building to dry out when conditions provide drying potential. In this section, we're going to look at heat and energy flow, as well as insulation strategies for managing this movement. As we begin to talk about managing energy in the building shell, we can start by looking briefly at the first and second law of thermodynamics. These rule how energy moves throughout the building, as well as into the building and out of the building, depending on the season. Remember, these laws are the basis for our basic principles. Warm moves to cold, more moves to less, and high moves to low. Calculating heat transfer through the building shell is a fairly straightforward formula. Heating contractors are performing this calculation whenever they do a heat load calc on a building using ACA Manual J. So in order to do this, we need to know how fast the energy will flow through an assembly. This rate of heat transfer is called thermal transmittance, and it's expressed mathematically as a U factor. The most common place to have seen a U factor is on a window sticker. U factors of windows tell us how fast heat transfers through the window and its frame. So we can use the overall U values of the building enclosure to determine how fast energy will transfer through it. The way to do that is to multiply the U factor by the area of the building shell and the difference in the temperature outside and inside the conditioned space. The result of this equation is the heating load. If we want to calculate the heat loss, we simply multiply the heating load by time elapsed. The important thing to remember about the U factor is that it's telling us about heat movement. It's energy in motion. In order to slow down that heat loss or gain, we need to use a barrier to interrupt the energy movement. Insulation is how we do that. The ratings of the insulation products expressed with R values tells us how well the insulation slows down the energy movement. R stands for resistance to heat flow, the opposite of the U factor, both in our buildings and mathematically. The R value is 1 divided by the U factor. So there's 3 modes of heat transfer: conduction, convection, and radiation. Conduction is when heat is applied to a solid material. Then it moves through that material to the colder parts of the material. The poker in this example is a great way to relate to conduction. If you leave that poker in the fire until the tip glows, the heat will move towards the cooler handle until it becomes so hot you need a glove to pick it up. In a building, this heat movement can happen through the wooden structure, from the warm inside to the cold outside in winter. Convection is heat moving with the help of other molecules, which can either be a gas or a liquid. And we're quite familiar with convective heat flow using a gas, and that's with air molecules. The heat warms the air particles, and then they rise when there's no other outside force to move them. And this is why most people think heat always rises, but it's not always true. Heat can move sideways or down. It's actually warm air that rises. We can see this demonstrated really well in a 2-story home where the second floor can get uncomfortably hot in the summer months. Radiation is heat moving electromagnetically with invisible waves of energy. Sitting in front of a fire, like in this example, we can feel the heat radiating sideways to our hands. And it works by line of sight too. When it strikes an object, there's a shadow behind the object, and most of the heat energy is absorbed by the object that's getting the radiation. Think of when you're at a campfire on a cold night, and you're warm in front, but your backside continues to get colder and colder, and eventually you need to rotate yourself to try to even out your comfort. In a building, radiation is easily felt at windows, with heat gain as the sun streams through, which of course is a benefit in the winter or a problem in the summer. So all of these mechanisms for heat transfer must be taken into consideration when building homes in order to optimize for energy efficiency and comfort of the homeowners. So let's look at each mechanism of thermal flow in more depth, starting with conduction. Thermal conduction is the movement of heat through a solid material. When the solid is exposed to a heat source, the molecules are activated or excited by the heat and then transfers that kinetic energy to the adjacent molecules. It continues like this with a domino effect through the material until it reaches the cold side, or what's labeled heat sink in this animation, and the heat will then radiate away. Here's an example. We're looking at an infrared image of a house taken on a cold night during the heating season. The framing is clearly visible because it is transferring heat by conduction or thermal bridging, appearing as warmer yellow in the photo, whereas the insulated stud bays are cooler, represented by blue. So to build a higher performing home, we need to minimize these thermal conductors that span from the inside conditioned space to the outdoors. Thermal bridging is a term you may have heard that describes this conductive heat transfer in a building. When we're looking at solid materials, there is a rating for heat transmittance called the K value, which is the rate of thermal conductivity. In other words, how fast does heat flow through the material? We can see in this table of building materials that metals are very conductive, with aluminum being the worst for heat transfer. A bit further down, we can see wood has a higher K value than insulation, listed as glass wool here, and that's what we saw in the infrared photo of the home on a winter evening. Radiation is energy moving as invisible electromagnetic waves. The energy is emitted nearly at the speed of light from a heat source. It moves in all directions until it hits an object, which then absorbs the heat. The object also creates a radiant shadow behind it. Radiation can work to our benefit for heating systems like radiant floor heat. But it can also cause some heat loss if we have open gaps in the insulation within our building assemblies. Convection is the transfer of heat by moving gases or fluids. In a home, of course, this gas is going to be air. It can act like a conveyor belt to move heat from a warm source to a cold heat sink. When this happens inside of a wall cavity, it will move heat out of the conditioned space in the winter and heat into the conditioned space in the summer, wasting energy for decades. And being inside of a wall, it's very unlikely that anyone will notice that air movement. So how do different building materials stack up for R value? Here's a list of insulating R values per inch. And remember, R stands for resistance to heat flow, the opposite of the U value, the speed of the heat flow. So still air has an R value of 6. And we often talk about creating a dead air space in the building cavity for insulation. And this is why air is a great insulator. Of course, that is air that's not moving has a high R value per inch. Some foams achieve an even higher R value by trapping special insulating gases inside the foam as bubbles. Fiberglass and cellulose achieve respectable R values if they're installed correctly to ensure there's no gaps and air is not moving through them. Again, we see wood has an R value of 1 per inch, but it's a fraction of what all the insulation materials can achieve. Concrete and soil have virtually the same low R value. And finally, we see steel with the least amount of resistance to heat flow. So let's get into the different types of insulation. The fiber-based materials we use for insulation is fiberglass, of course, cellulose, rock wool or mineral wool, and less typical but viable is cotton insulation or wool insulation. And the fiber insulation products can be installed a number of ways depending on the product, from loose fill blown in, bats and blankets, blown in systems like bibs, spider, or dense pack, and open cavity spray. And by far the most challenging type of insulation to install correctly is the bats or blankets. They must be custom cut and fit around all the surfaces installed in the wall, like the electrical and plumbing. And then varying stud bay sizes also requires a custom cut. It's rarely done to the same quality install that you can get with one of the spray-in or blow-in materials. So why are those imperfections in bat insulation so bad? Well, the gaps and spaces dominate the heat loss. No matter how much insulation you pile up next to a gap, the heat loss through the gap is not reduced at all. And the larger your initial R value is, the greater the effect it will have on lowering the R value of the building assembly. In this chart, you can see the effect on walls insulated with bat insulation. The rated R value of the insulation is severely degraded when the bats are installed poorly. And unfortunately, this is the quality of a typical installation. So here's an example to show us how a small area can have a huge impact on the overall performance of a building assembly. You can crunch numbers through a formula called a weighted area average to see this. So imagine we have a 1,000 square foot attic insulated to R38 and 5 square feet insulated only to R1. And this 5 square feet is the attic hatch because the bat sitting on the back of the attic hatch was tossed aside and not put back in place. How is the heat loss through that hatch affecting the overall R value of the entire R38 attic? After all, 99.5% of the attic is still insulated. When you run the numbers, it shows the attic is now performing as if it only had R32 insulation, just because someone forgot to put the bat back in place. So this illustrates that a wall with a lot of little gaps in the bat insulation could have its R value degraded severely. So if you are committed to using bat insulation, it's crucial that it is installed as perfectly as possible, and that means contact with all 6 sides of the stud bay. It should fill the entire cavity without any gaps or voids, and without compression being stuffed behind objects in the stud bay that compresses the insulation and also degrades its R value. Unfortunately, it's often installed like this, not cut precisely around boxes, plumbing, or other objects, compressed behind wires, and gaps that provide line-of-sight pathways from the warm sheetrock to the cold exterior sheathing. Here's another IR photo that shows heat loss because a bat was compressed behind a wire and cold air is leaking through that void, creating a very cold area across the wall. So the easiest way to overcome these challenges is to move over to a different type of insulation. Blown-in wall insulation is an awesome choice. It prevents these voids by flowing around all the objects in the wall during installation and creates a high-quality assembly that performs to its rated R value. It can also reduce air movement by filling the entire cavity so that the insulation is in contact with all 6 sides. Another benefit of blown-in insulation is that for many of the products, you end up with a higher R value. For example, with a 2x6 stud wall, you can end up with as high as an R23. Here are some photos of walls insulated with blown fiberglass behind a fabric netting that is stapled to the studs. Floor insulation is typically done with fiberglass bats and often suffers from the same defects found in walls, with voids and gaps. Some builders are having their floors blown when there is adequate height access, but typically bats are still the go-to for most projects. It's key to make sure the insulators do not build in compressions, gaps, or sagging floor insulation. It needs to touch the bottom of the subfloor to be effective. So when installing the support for the bat insulation, it must be done so that the bat is making contact. Otherwise, cold air can flow between the subfloor and the top of the bat, hanging too low. This can effectively degrade the floor insulation to an R0 in a worst-case scenario. This is a situation that really requires blown-in insulation. An open web floor joist above a garage with a conditioned bonus room above the garage. We can see that the truss creates a 3.5-inch gap at every joist, allowing for heat loss. But since the floor is above a garage, the insulators have access to net it and blow the insulation into these cavities to fill the entire assembly. In attics these days, the norm is now blown insulation, and as long as the installer does a good job of getting the required height and the proper bag count for the attic area, it provides an excellent thermal boundary. Of course, it's key to keep people from disturbing it and creating compressions or voids. Bats installed in attics of existing homes of course often look like this. A good retrofit solution is to add a layer of blown fiberglass or cellulose over these bats. Cellulose is another fibrous blown type of insulation, and it's installed in one of two ways: as a loose blown-in for open attics, or at a higher density when installed in walls. The higher density in walls is often referred to as a cellulose dense pack, and it's done this way to prevent settling over time. Settling did happen in the early days of blown wall insulations because it was not blown into a higher density. Now the industry understands the density required for both cellulose and fiberglass insulation, and there's no need to be concerned about settling any longer, as long as the installer is using the accurate bag count for a dense pack. Here's a shot of cellulose installed in an attic. Now let's look at exterior insulations. By adding a layer of continuous, rigid exterior insulation, you can increase the R value of the wall significantly. The insulation itself adds more R value over the cavity, but the other big improvement is that it insulates the framing studs, plates, and headers, essentially putting a barrier or break in the thermal bridge to stop that rapid heat movement by conductive transfer through the wood. There are many types of foam board insulation and mineral wool insulation that can do the job. The rigid insulation types vary in their R value per inch, as well as their permeability, their ability to allow for drying. It's important to consider both of these characteristics in your wall design so that you build an energy-efficient wall that also has good drying potential for long-lasting durability. Spray foam is another insulation option, and it has many benefits. It provides excellent air sealing, as well as an excellent fit. It flows around all the obstacles in the walls. Even if there are small voids, it's not a problem, as the whole cavity is air sealed. It provides high R values per inch, depending on the density of the foam, and the vapor transmission or the permeability also depends on the density of the foam. And spray foam has been more typically used for a whole house installation with higher budget projects due to its cost. There are two types of spray foam, low density and high density. The low density has an R value of 3.8 per inch, and it's vapor permeable. The high density has a higher R value at 6.8 per inch, and it's vapor impermeable. Once again, it's key to pay attention to these very different perm ratings. The low density provides drying potential, but the high density does not at all. That doesn't mean you would never want to use high density impermeable foam. It has its place, like in insulating a basement wall or building an unventilated and insulated roof to bring the attic into conditioned space. Spray foam can be a great solution for challenging areas of the structure to insulate and air seal. Places like band joist areas, rafter ceiling joists, wall intersection, and other places. And this is called targeted spray foam. It can be installed at a more affordable price point by buying what is known as a froth pack, which is designed for targeted applications. Spray foam can also be used in combination with bat insulation to do what's known as a flash and bat install. 2 to 3 inches of foam are sprayed into the stud bay, and then the bat fills the remainder of the cavity. The spray foam insulates and air seals, and if the air seal from the foam is done well, then the bats work okay since the voids do not have a source of air. As you can imagine, this allows the use of spray foam at a more affordable price point. The example we see in the photo is the installation of what I was just referring to earlier, where you use high-density spray foam against a basement wall, followed up by a bat. The high-density spray foam provides moisture protection from the moist basement wall when converting a basement to a living space. Aside from cost, some builders avoid this product because many spray foams have a very high global warming potential due to the type of gas used as a blowing agent. This graph shows how if you considered the energy saved and the carbon emissions avoided by the insulation over the course of its use in the home, then calculate in the global warming potential of the gases used in the foam and the embodied energy to make the insulation, you get an overall global warming payback in years. You can see both spray foam and XPF rigid foam have a very long payback of around 90 to well over 100 years. If you contrast that with the other insulation types, which are less than 10 years, it's quite a big difference. Not all spray foams use blowing agents with high global warming potential. There are foam manufacturers that have developed very low global warming potential agents, so there are choices for spray foam to have a more positive impact on global warming. So we've covered why we want to build high-performance buildings and the building science of what we need to control, so now we're ready to get into the how to achieve high performance. We're going to start looking at 10 categories of high-performance buildings. And as a quick reminder, we'll look at examples of materials, techniques, strategies, and equipment organized into good, better, and best categories, each of which can be thought of as a progression of more energy saved with each level. Number 1 is design for efficiency. Buckminster Fuller, a famous 20th century architect and visionary, said that the best way to predict the future is to design it. As builders, you have a great profession where the work you do has a direct and lasting effect on the future. Not everyone can say that about their work. You also know that good design and planning leads to more successful projects and better profits. So of course it's true that good design and planning will go a long way towards helping you build high-performance homes. Okay, so what do we want to do to design for efficiency? At the good level, we want to build with a continuous thermal boundary. To take it to better, add right sizing of design and systems. And then at the best level, add optimization of the design with energy modeling. A continuous thermal boundary is simply making sure that the boundary between conditioned space and unconditioned space has no gaps at all in the insulation or air barrier. As the geometry gets more complicated in a project, the likelihood of having a gap in the boundary increases. Additionally, it's crucial that the air barrier aligns precisely with the insulation at the thermal boundary in order to protect the insulation from degradation of its performance and R value. And we'll talk more about this in the next section on air sealing. In our heating-dominated climate zones, we want to optimize our design for solar gain in the winter. So when possible, design the largest area of windows facing to the south to capture the free solar heat in the winter. To optimize south-facing windows, they should have a solar heat gain coefficient of greater than 0.6 to maximize solar heat gain during the winter, a U factor of 0.3 or less to reduce conductive heat transfer, and a high visibility transmittance for good visible light transfer. Good design also includes locating rooms that are most often occupied and have the greatest heating and lighting requirements to be along the south face of the building when possible. At the better level, we want to minimize energy loads and right-size the building and the systems. That means minimizing envelope heat loss and gain, keeping the window to floor area ratio as low as possible, minimize air infiltration, and on the conditioned floor area, avoiding square footage bloat. If you can meet the needs of your customers with slightly less square footage, it makes a big difference in the overall energy needs of the building. And then we want to optimize the design to capture the benefits from the natural forces where we can. That includes solar gain and natural light, taking advantage of the stack effect, which is when warm air rises within the building, so this can be used to help cool the building if you provide a place for the warm air to escape at the top, like operable windows or skylights high on the structure. Taking advantage of prevailing winds to help cool the building again. Cross ventilation, operable windows on the typically windy side of the home in summer will allow for breezes to literally blow through the building and cool the home. And then right sizing of mechanical heating and cooling systems will save on initial install cost and provide a system to the homeowner that will run to its optimum performance for comfort and lower operational costs. To take the design strategies to the best level, you complete all of the steps in the good and better, and then you add energy modeling. This is running your plans through a computer simulation model that will predict how much energy the home will use during its operation. It's an analysis of heat loss, heat gain, air leakage, mechanical efficiency. It assumes typical occupant behavior and a typical number of people living in the home. And you can analyze different upgrade measures to select the optimum package, design and meet your customers' needs, and of course, keep the design in the right price point. Contact your local energy rater verifier, who can often provide this service for you. The energy modeling will give you the ability to, in effect, turn the knobs up or down on your upgrade levels. Some of the elements you can analyze and adjust are the shell measures of insulation, the amount of air sealing, the number and type of windows. And on the equipment side, you can adjust the heating and cooling efficiency, the water heating efficiency, and solar can be modeled in these energy models to predict how much electricity could be produced to partially or fully offset the energy used in the home if you're trying to achieve a zero energy or zero energy ready home. Our second top 10 best practice category is superior air sealing. At the good level, we're looking at code level caulking and sealing. To take it to better, adding a fully continuous air barrier. And for the best category, exterior sheathing sealed to move the air barrier to the exterior. Air leakage can account for up to 30% of heat loss in a typical home. It can degrade the insulation's ability to resist heat flow, and it can move heat directly by convective heat transport. It can also transport moisture, reduce comfort levels, increase air pollution, and be one of the largest causes of ice dams. Here we see an example of how air can transport moisture into an attic. Cold moist air is flowing up through the walls and onto the bottom of the roof deck, frosting up the rafters. Ice dams happen once in a while here, particularly east of the Cascade Mountains in climate zones 5 and higher. Warm moist air flowing up a wall or through ceiling gaps and holes, along with low levels of attic insulation, which can also contribute to heat making its way to the underside of the roof, causes the snow on the roof to melt. It then runs down the roof until it refreezes at the cold eaves. The ice can then work its way up under the shingles and even enter the attic in really bad ice dams. This, of course, can now remelt into the attic and down into the living space, causing a real mess. The best fix is to air seal and insulate the attic so that the snow does not melt from internal heat loss. You solve energy waste and solve the ice dam problem at the same time. Air movement, as we covered earlier, is governed by one of our fundamental principles, that it moves from high pressure to low pressure. Those pressure differentials will always even out over time. So what causes these pressure differences to be higher or lower in the first place? Well, there's a number of things that cause pressure differentials almost daily in our buildings, and we call these driving forces. One example of a natural driving force is what's known as the stack effect, causing high and low pressures in the home. In the winter, as air molecules are warmed by the heating system in the home, they rise up through the structure in the same way gases move up through a flue vent or a smokestack. That's where the name stack effect comes from. The rising warm air creates a high pressure zone relative to outside, high in the building at the ceiling plane and upper portion of the walls, and a low pressure zone at the lowest floor plane and the lower parts of the walls. So during the heating seasons, the stack effect driving force creates these pressure differences, and if there's leakage paths, the high moving to low will pull air into the home at the lower openings and push air out of the home through openings higher in the building. In this photo, we can clearly see the stack effect in action on a cold winter day. This commercial building's under renovation, and there's a fabric covering the scaffolding, and it's been put up where the building's been opened for work to try to keep some heat in the space for the people working on the building. You can clearly see the high pressure billowing the fabric out at the top of the scaffolding, and the low pressure sucking the fabric in to the scaffolding at the bottom. Now near the mid-height section of the building, there's a place where the negative pressure switches to positive pressure, and this spot's called the neutral pressure plane. It's the same pressure inside as outside at the neutral pressure plane, so there's no driving force. In single-story buildings, this usually happens around chest height where the windows are located. Wind is another natural driving force that will cause high and low pressures. When it's blowing outside, the windy side of the house will experience high positive pressures relative to inside the conditioned space. And on the leeward opposite side of the house, protected from the direct wind, the house will experience low, negative pressures relative to inside the conditioned space. Driving forces can also be introduced by our mechanical systems, more specifically, our forced air heating and cooling systems. The fans driving the forced air systems are powerful and can create areas of positive or negative pressures within the home. And one way this happens is when there's no clear path for the supply air to get back to the return grill. This usually occurs when people close internal doors to bedrooms. The bedroom behind the closed door will become positively pressurized relative to outside, and the zone where the return grill is located in the rest of the house will go negative. This can cause the air in the bedroom to flow through cracks and gaps and possibly drive moisture into the building assembly along with the air. In the main body of the house where the return grill is located, the negative pressures can then draw air in from cracks and gaps from crawl spaces, attics, or outside into the conditioned space. The other way forced air systems can get out of balance is if the ductwork is leaky, and the ducts are located outside of the conditioned space, which they often are, being in attics, basements, and crawl spaces. The air leaks from the ducts throw the system's delivery and return pressures out of balance with respect to each other. Again, this can create driving forces across the entire conditioned space, either negative or positive, and that depends on where the leak is located, if it's in the supply ducts or the return duct. So now that we've covered the driving forces, let's look at the other element for air leakage, and that is a path. Where does air leak? Well, aside from the holes and cracks in the studs or the plates of the building shell, there are other typical places that air will find a path to move through. At transitions between building surfaces where one material meets another, and then at intersections where walls, floors, and roof lines meet, and then in empty spaces within the walls or other building assemblies which are hidden by drywall. Things like chases for a fireplace flue stack or a chase for ductwork where the ducts are moving from one floor to another are another classic spot where air can find a clear path to move from one level of the building to another, following those pressure differentials created by the driving forces. So here's a great example of where the wall plane is meeting the floor plane and the wall plate was not sealed to the subfloor. Air is flowing in, and we can see in the IR image where the blue color indicates a cooler airstream flowing right underneath that baseboard trim. So this is where we want to use either a sill sealer gasket to prevent this leakage or some sort of flexible caulk or foam to seal that crack where those two planes meet each other. Another common problem area for air leakage is under knee walls, where air can flow into the floor cavity of a half-story level or a bonus room above a garage. The ventilation air for the roof and attic can be pulled into that floor cavity because there's a break in the air barrier along the thermal boundary. In this drawing, we can see the blue dashed line represents that air barrier, and there's a break in the air barrier right there where the arrow is showing how air can flow through that break and into the floor cavity. Another typical leakage area is where duct boots, fan housings, or lighting and electrical boxes are cut through the sheetrock. When you're using the sheetrock as the air barrier, these penetrations need to be sealed with caulk, foam, or a gasket to close these paths for air leakage. This, of course, is also true for any penetrations that are cut through the subfloor. So back to our good, better, best for air sealing. To achieve the good level, you simply can follow the prescriptive requirements in your state building code. Or if you're working in a state without air sealing prescriptive requirements in the building code, you can find an air barrier installation list in the latest version of the International Energy Conservation Code, IECC, Chapter 4. All of the penetrations through the floor, ceiling, top and bottom plates, and through the wall cavities need to be air sealed with foam or caulk. So do the rough openings around windows and doors. Open chases that we just talked about need to be sealed at the top and bottom to stop large amounts of air movement, and of course this is also required by fire code. And then using a blown-in insulation product in the walls can also provide a small amount of air sealing as a secondary benefit to the insulation itself. At the better level, we air seal with the focus of creating a continuous air barrier with alignment to the insulation. This is essentially taking good air sealing strategy and using a checklist tool like the Thermal Enclosure Checklist, commonly referred to as the TEC. It was developed by the Energy Star for Homes program. If you use this checklist, it will help ensure there are no hidden gaps in the air-sealed thermal boundary. One example of this in the TEC is that it prescribes adding a gasket to the top plate, as we see in the photo on the right. You can also use a bead of caulk between the top plate and the sheetrock to seal this common place for air leakage. As the top plate dries out, it shrinks and often opens a crack, which creates a path for air leakage from the wall to the unconditioned attic. And this gasket or caulk will help prevent this. Other places you'll focus on at the better level using the TEC are behind fireplace surrounds and behind tubs and shower enclosures by adding a rigid material, picture frame sealed with foam or caulk at the edges, to keep a continuous air barrier running next to the insulation. Traditionally, the insulation is open and exposed behind these areas. The air barrier must also be continuous behind soffits, again so that it's touching and protecting the insulated cavity. You also want to make sure you have a continuous air barrier under and behind staircases. On the back side of cathedral ceiling knee walls that face the ventilated attic, these short triangular walls on the top of interior walls are essentially exterior walls dividing inside space from outdoor air and temperatures. Skylight well shafts can be very tricky to create a six-sided air-sealed wall cavity to protect the insulation, particularly when framed in using flat truss members. The typical solution is to use rigid foam insulation as puzzle pieces to fill in these triangles and get the needed R value. The rigid foam is not vulnerable to air infiltration from the attic, so it's a good way to tackle this problem. Alternatively, using tubular daylighting skylights can be an even better way to light a dark space because you can get an air-sealed and insulated type of tubular skylight that provides good light with a smaller area, resulting in less heat loss, and of course no challenge dealing with the shaft air sealing. The TPC will also address the common knee wall problem that we looked at earlier. Blocking will be installed with air sealing around the edges to protect both the floor cavity and the top of the knee wall from any air infiltration. A solid sheeting material is also installed on the back side of the knee wall to create the six-sided box that protects the insulation. If you're currently installing FSK paper in places like behind tubs and fireplace surrounds for fire code, you'll want to cover it with a solid sheet material and picture frame seal around the edges for a robust continuous air barrier that'll last over time. Taking air sealing to the best level, there's a couple different approaches you can take. The first is to add a second air barrier to supplement the first one at the air-sealed drywall. Here we see an example of adding a second air barrier on the exterior by using a specialized tape to seal up all the seams and cracks on the outside of the building. This is the belt and suspenders approach because you seal both sides of the wall. There are some manufactured products like Huber's zip wall system that creates a robust exterior air barrier, as well as a weather-resistive barrier and structural sheathing all in one. It also uses a specialized tape for sealing up the seams. Another example is Henry Blueskin, which is a self-adhering weather-resistive barrier, which also provides exterior air sealing. Many Northwest builders are having good success with liquid-applied weather-resistive barriers to lower their air leakage numbers significantly. These products can fill in all the seams and gaps to protect the walls from liquid water, and this also does a great job at creating a tight exterior air barrier. One key detail when you go with an exterior air barrier is how to tie it into the air barrier at the floor and ceiling planes, in those transition zones we talked about earlier where air leakage often happens. At the foundation, you want to make sure the air barrier connects to the foundation. You can use a liquid-applied sealant, air sealing tape, or flexible flashing, basically anything that's capable of adhering to both wood and concrete and is air impermeable. Some products will require a primer to improve that adhesion to the concrete and wood. At the top of the wall, the air barrier needs to round the corner and tie into the ceiling plane to be continuous. One solution is to use a wide strip of the weather-resistive barrier or a similar air barrier product to wrap around the corner. The material apron temporarily hangs down over the inside of the wall and then is tied into the ceiling air barrier after the trusses are installed. But how do you install the trusses without having to cut this air barrier to ribbons for the hurricane clips that secure the truss to the top plate? One of the easiest solutions to this challenge is to use truss screws. Simpson's Strong Drive truss screws or Fasten Master Timberlock wood screws are two examples that can attach trusses or rafters to a double top plate via a screw driven at an angle from beneath the top plates into the trusses or rafters. This code-approved methodology eliminates the need for hurricane clips and avoids a potential air sealing nightmare. Some builders are taking the ceiling plane to the next level by using taped OSB air barriers across the ceiling behind the sheetrock. This OSB air barrier on the ceiling extends over the top plates and ties into the OSB wall sheathing. The corner is air sealed with wide air sealing tape or self-adhered flexible flashing or the WRB material. A second approach to the best air sealing level is to add a dedicated layer within the wall to act as the primary air barrier. There are a number of fabric type air barriers and tapes which have proven to be very effective. Many of these products were originally developed as part of the Passive House movement in Europe. Passive House certification requires very tight air sealing, and these air barrier systems can deliver the results. They're usually installed directly behind the sheetrock or within the wall in a dedicated service cavity just behind the sheetrock. Or if you're building a double stud wall, they can be installed inside the wall on the back side of the inner studs to protect the air barrier layer. Finally, we're also including a relatively new material and technique as an innovative approach to the best air sealing category. AeroBarrier is a flexible air sealant that is installed after the building shell is complete with windows and doors installed and the lid hung. It goes in as an aerosol mist while pressurizing the house with a blower door fan, which causes all of the air to flow from the interior to the exterior. The small particles of air sealant flow with the air through the cracks and gaps across the entire building shell and then stick to the edges of the materials where the air is flowing. It builds up until it forms a barrier that seals up the air path. This can save labor costs of manually sealing up all of those pathways. The building gets tighter the longer the air sealing system runs, and you can simply order your desired level of air tightness. So how do we measure our success with our air sealing efforts? Well, that's with a blower door. The blower door test is a service provided by your third-party verifier as part of certifications and energy efficiency programs. It works with a large, powerful fan which is set up in a doorway that pulls all of the air out of the building and then measures the quantity of air leaving the building through the fan. And this shows how much air is leaking in through the pathways in the building shell. The test result is then measured in what's known as air changes per hour, or in other words, how many times will all of the air in the house be pulled out with the fan in 1 hour. It's a great tool to not only measure success, but it can also be used to find and seal leaks if pathways are accessible. It's used for both the new construction and for energy upgrades in existing homes. So what numbers do we see in blower door tests of high-performance homes? Here's some air tightness levels for comparison. All of these numbers are expressed in ACH 50, which is air changes per hour at 50 pascals, and that's the test conditions for a blower door. A typical Oregon Code level new home tests around 6 to 7 ACH. The Washington State Energy Code requires a new home to be 5 ACH or lower. Energy Star new homes requires 4 ACH or lower. The average for Earth Advantage homes certified in 2019 was a 3.1 ACH. And then Passive House certification requires a 0.6 ACH or lower, which is one of the most stringent of all programs in the US. The tightest tested by Earth Advantage staff was 0.19 ACH 50, and the tightest tested in the US was 0.05 ACH 50. So how tight is too tight when it comes to buildings? Many people are concerned with air sealing a home and creating either an unhealthy environment with stale polluted air or a building that's vulnerable to moisture and decay. As the old saying goes, buildings need to breathe, and that's usually followed by I'll never build one of those tight houses. But this is a misunderstanding of building science and the goals of building tight. The buildings don't need to breathe. Buildings need to dry out. And that's why it's crucial to build with materials that have high permeability to allow for drying for the long-term durability of the structure. It's people that need to breathe fresh, clean air. And that's why air sealing must be done in combination with installing a fresh air ventilation system, so the occupants don't get sick from poor indoor air quality. If you have an older leaky building that quote-unquote breathes, what you have is random leakage from uncontrolled locations, and this uncontrolled air can bring in more pollutants and more moisture into the building. So by air sealing the building, we take control. We stop random air movement and introduce a controlled ventilation system with the correct amount of air from a known clean location. And this is how air tightness improves ventilation, indoor air quality, and potentially durability by keeping out moisture when humidity is high outside the structure. We'll cover more about good, better, and best whole house ventilation systems in Section 7.